We're currently witnessing the greatest capital expenditure boom in human history. Microsoft, Google, and Amazon are pouring over $100 billion into data centers this year alone. They are buying the most advanced silicon chips in the world. But there's a dirty secret in the hardware industry that nobody discusses. We are hitting a physical wall. And that's why, while everyone is looking at the stock prices of the big names, I'm looking at their electricity bill. We've been trying to build thinking machines using an architecture designed in 1945 to build calculators. It is called von Neumann architecture. It separates memory from processing. To do a calculation, data has to travel back and forth. This travel generates heat. Heat requires cooling, and cooling requires massive energy. In fact, nearly 40% of the energy consumed by a data center isn't used for computing at all. It's used just to keep computers from melting. Billions of dollars of investor capitals are being burned essentially to run air conditioners. Welcome to Growth. I'm Sean, your guide to money and navigating the frontier of innovation. First, we have to answer the skeptic's question. Why can't you just make silicon chips smaller? We've done it for 50 years. Moore's law. The number of transistors doubles every 2 years, right? Here's the problem. For decades, shrinking a transistor made it more efficient. But below 5 nanometers, the rules of quantum physics start to emerge. At this scale, electrons don't just flow, they leak. Even when the chip is supposed to be off, power is draining away. But the bigger issue is the clock. Standard silicon chips operate on a global clock. Every nanosecond, the chip wakes up, checks the states of billions of transistors, and asks, do I need to do anything? Even if the answer is no, that check costs energy. This is called clock-driven computing. It is incredibly wasteful. Your brain does not have a clock. It is event-driven. It only fires when something changes. So how do we fix this? The smartest engineers at IBM and Intel are trying to solve it by changing the map. They are building neuromorphic chips using standard silicon. Intel is doing this under Loihi 2. IBM is doing it under North Pole. And they work. It is vastly more efficient than a standard CPU. But they are still using transistors to simulate a neuron. To make a silicon chip act like a brain cell, you have to build a complex circuit of 20 or 30 transistors just to mimic what a single biological cell does naturally. It works, but it is complex. If you want to go to zero energy, we don't need a better simulation. We need a material that is a neuron by default. This is where we leave the architects and meet the alchemists. We're looking for a material that naturally performs one specific function: integrate and fire. It collects energy, spikes, and resets. And right now, there are several contenders fighting to be the building block of the synthetic brain. The first one is Mott Insulator. Think of this as a traffic jam. In Mott Insulator, electrons are strongly correlated so that they get stuck in the material, repelling each other. But when applying a tiny voltage, the traffic jam clears instantly. It snaps from insulator to metal, releasing a spike of electricity. The second is spintronics. This is pretty heavy hitter. Instead of moving electrons, which creates heat, in spintronics, they flip spin, the intrinsic magnetic state of electron. Big companies like TDK are building spin memristors that consume 99% less power than silicon. And there is the wild card, biological computing. Some researchers are asking, why simulate the neuron when you can just use the neuron? This isn't a science fiction. Cortical Labs, an Australian venture, has already grown human brain cells on a silicon chip that learn to play Pong faster than an AI cloud. And Final Spark in Switzerland just launched a platform where you can rent access to a human brain organoid via the cloud. They claim it consumes 1 million times less energy than silicon. We don't know which materials will win or even ever scale, but we know what they all have in common. They replace 30 transistors with one single device. This is how you get density and efficiency. So, how does this solve the energy problem? It solves it by allowing us to disconnect from the cloud. Right now, if a robot sees an obstacle, it often sends video to a server to process it. That data transmission costs 100 times more energy than the computation itself. With neuromorphic chips, we get something called edge AI. Because these chips are so efficient, we can put the AI on the sensor itself. Imagine a security camera. With a standard chip, it processes empty footage 24/7. With a neuromorphic chip, it sits dormant. Only when a threat walks in, it wakes up, recognizes the threat, and alerts you. If nothing happens, it costs almost zero energy. This is how we put intelligence into devices that run on coin batteries for years. Now, let's follow the money. The neuromorphic computing market is projected to surge from $1.7 billion today to nearly $9 billion by 2034. That is an astonishing 18% annual growth rate. However, there are actually several sectors being developed at the same time. First, you have silicon optimizers. These are the giants betting we can just rewire the old chips. Intel is leading with Loihi 2. Look at their partnership with the National University of Singapore. They made electronic skin that feels touch 10 times faster than a human nerve. They're also engaging lead customers on their new Intel 14A process nodes, preparing to mass produce these architectures. IBM has North Pole. In recent benchmarks on the YOLO V4 Vision model, it hit 969 frames per second while consuming just 74 watts. That makes it roughly 25 times more efficient than a standard GPU. Also, there's a startup, SynSense, a venture company spun out of ETH Zurich, recently closed a Series A round to deploy the tech into smart toys and security cameras in the Chinese market. They are already commercializing with partners like Innovation for eye tracking. Next, material revolutionaries. These are the players betting that silicon itself is the barrier. TDK is the dark horse. They are pivoting their massive magnetic component business into spintronics and edge AI. They just announced a showcase of physical AI technologies for CES 2026. They are waking up. HPE remains silent giant. They hold the foundational patent for the memristor from their 2008 discovery. They own the blueprint that everyone else is trying to build. And then there is biological ones. This is the sector that most investors are too scared to touch. But there's something to watch. Cortical Labs officially launched their CL1 system in March 2025. It's a synthetic biological intelligence server stack priced at $35,000, allowing researchers to run code on living neurons. Final Spark in Switzerland has launched the Neuro platform, where you can rent access to 16 brain organoids for $1,000 a month. And a research team from the University of Bristol just published a preprint in Archive using this platform for real-world tasks. So, here's the verdict. We're standing at a massive divergence point in the semiconductor market. On one side, you have incumbents, Intel and IBM. Their strategy is optimization. They're betting that the global supply chain is too entrenched to change. So they are rewiring the old silicon to be good enough for the edge AI. This definitely has higher probability. On the other side, you have the disruptors. Their strategy is transformation. They're betting that good enough silicon is not enough. They're betting that as we demand always-on intelligence, the cost of energy becomes the only metric that matters. But to be honest, this is a brutal bet. Physics is messy. There is a reason we stuck with silicon over 50 years. It is predictable. Materials like Mott Insulators, spin memristors, or even biological neurons are volatile. They are hard to manufacture and hard to control. Especially the lab-to-fab gap, the chasm between a working prototype and mass-produced chip, is where more than 90% of these companies will die. So the question for you is this: do you believe the future of AI belongs to massive centralized data center? Or do you believe the intelligence will inevitably decouple from the cloud and move to the device on your pocket? I want to hear your take in the comments below. This was Shun from BySpark. If you enjoyed the video, press like, subscribe, and hit the notification button. And if you want a written version of this video with full references, subscribe to our newsletters. Thank you for watching. Until next time.